Let's next see number 14, where we have a non-zero ring A and sigma is the set of all ideals of A, where every element is a zero divisor. We have to show that then sigma has maximal elements, at least one maximal element, and here maximality is with respect to the containment relation, and that each maximal element is a prime ideal. We start the solution by considering this partially ordered set sigma, ordered with ordinary set inclusion, that is subset relation. And the first thing we note is that sigma is non-empty because 0 belongs to sigma. What is this 0? Actually this 0 is the 0 ideal, where the only element is 0, which is a 0 divisor. So by the definition of sigma, this really belongs to sigma. So that means we are looking at a non-empty partially ordered set. So next, let K prime be a chain in sigma. You recall that a chain in a partially ordered set is a subset which is totally ordered, where any two elements are comparable. And you also understand where this is all going. We want to be able to apply Zorn's lemma to this non-empty partially ordered set, for which we need to first of all show that every chain has an upper bound in sigma. So K prime is one such chain, and let K be the union of all the elements of K prime. So that means these are ideals in K prime. Not necessarily all the ideals in sigma, but in that subset K prime, which is totally ordered by this set inclusion, that's why it's a chain. We collect all the ideals in K prime and take their union. Let that union be K. To cover all the cases, we have to also include this case where K prime is empty. Note carefully that the empty set as a subset of sigma is also totally ordered. Not only is it partially ordered being a subset of sigma, but actually it's totally ordered. So that means it can happen that K prime is empty. If so, then the zero ideal, which is already an element of sigma, is an upper bound for K prime. You try to apply the definition of this being an upper bound for K prime in this case, that K prime is empty. You will see that the definition or the condition is true, vacuously true, but nevertheless true. So that means in this case, yes, K prime has an upper bound in sigma. So next we assume that K prime is non-empty. And in this case, K then becomes non-empty. Why? Well, what is K prime actually? K prime basically is a set of subsets of A, where A is our ring. And these subsets are ideals actually. So K prime being non-empty means that there is at least one ideal in this collection that we are taking the union of. And that ideal itself is non-empty because at least it has the zero element. There may be more than one elements in K prime, but there is at least one ideal, and that ideal has at least one element 0, which will then belong to K. So that way K becomes non-empty, and in fact K is a non-empty subset of our ring A. Now we aim to show first that K is itself an ideal. So for that we choose two elements A and B in K, any two elements. Then because these elements belong to a union, so for each one of them there will exist at least one set in this collection that will contain it. That means there will exist I and J in K prime such that A belongs to I and B belongs to J. I and J need not be the same, okay? And this is where the fact that K prime is a chain will be used. Because K prime is a chain and I and J are coming from K prime, so they are comparable with respect to the set containment relation, that is subset relation. And that is why we can assume without loss of generality that I is a subset of J. But then B is already in J, whereas A being in I will also be in J. So that way we now have the fact that A and B are two elements in J, and J is an ideal. And because of that, A minus B belongs to J. Because J is an ideal, so it's a subgroup of our ring under addition, which implies that A minus B belongs to K. Why? Because J is one of the sets in the union which is K. That is why. And this proves that K itself is a subgroup of our ring under addition. Also, if you take an arbitrary ring element small c, say, and multiply this element A by C, then AC will belong to I, because A belongs to I and I is an ideal, so the product AC will belong to I. But then because I is just like J, one of the sets in the union K, so AC will automatically belong to K. And that's how we have proved that K is actually an ideal of A. Moreover, clearly every element of K is a zero divisor. Why? Because K is a union of ideals where in each ideal every element is a zero divisor. So automatically all the elements of K will be zero divisors. But then K qualifies to itself be an element in sigma. And obviously then K becomes an upper bound for our chain K prime in sigma. Why? Because K is the union of all the elements in K prime. So each element in K prime is a subset of K. In that sense, with respect to the subset relation, K becomes an upper bound. But then now you can apply Zorn's lemma. So by Zorn's lemma, this partially ordered set has at least one maximal element. There may be more than one, but there is at least one. In the second half of the solution, we have to show that all the maximal elements in sigma are prime ideals. So let P be any maximal element in sigma. Clearly P is an ideal because that's what sigma has, ideals. So maximal elements also after all are ideals. But suppose P is not prime, and also note that P is a proper ideal. Why? Why is it that P cannot be equal to the entire ring? That is because if P equals the entire ring, then P also needs to contain the multiplicative identity 1, right? But 1 is not a zero divisor, and that's because 1 is not equal to 0. In the zero ring, 1 is equal to 0. But you go back and see the exercise, A is a non-zero ring. That is why. So, because P is already a proper ideal and we are saying that it's not prime, that means the condition for primality should be violated. So, we will find elements A and B in P, neither of which belongs to P, but their product belongs to P. This goes against the condition for primality. Primality says that if such a product belongs to P, then at least one element has to belong to P. Now what we do next, we consider these following ideals. The sum of P and the principal ideal generated by A, and the sum of P and the principal ideal generated by B. Say this one is I1 and this one is J1. And this is what we naturally found about these ideals, that both of them contain P, but P is not equal to any one of them. It's obvious that I1 contains P as a subset of it. However, at the same time, I1 also contains the element A. Do not forget that our rings have identity elements, multiplicative identity. So all the multiples of A are present here. In particular, 1 times A is also there. So that means A is there. A, however, is not in P. So that way, besides being a subset of I1, P is actually a proper subset of I1. Just like that, because B is not in P, J1 contains P properly. However, what is P? P is a maximal element in sigma. So these things being greater than P in that sense, in the sense of containing, they cannot belong to sigma. Now what type of elements does sigma have? Sigma has those ideals where all the elements are zero divisors. These are ideals. Okay, that fact is there. I1 and J1 are both ideals. So that means they are not that type of ideal. Each one of them will then have an element which is not a zero divisor. Say I1 has this x and J1 has y, which are not zero divisors. Now, because x and y are coming from I1 and J1, their structures tell us exactly what type of elements these are. X has this form, P1 plus alpha A. Why? Because I1 is the ideal P plus the principal ideal generated by A. So this X will be a sum like this of some element P1 in P and some multiple of A, where the element alpha of course is coming from our ring A. Similarly, Y is P2 plus beta P, where P2 is some element in P and beta comes from A. Now next what we do, we take the product of X and Y. Using all the ring axioms, the product becomes this, the right hand side if you do multiplication. P1 P2 plus P1 beta B plus alpha A P2, but because multiplication is commutative, you can write P2 alpha A, or you can actually write anything. In any order you can write the product plus alpha beta AB. Now note that P1 and P2 are both coming from P, so P1 P2 belongs to P. Next, what about this second term? Because P1 is already in P and P is an ideal, so this product of P1 with this some other element beta P is also inside P. Just like that, P2 alpha A also is inside P, again because P2 belongs to P and P is an ideal. And this is also inside P, because if you go back and see the conditions put on the elements A and B, individually they are not inside P, but their product AB belongs to P. So the multiple of AB by alpha beta also belongs to P, again because P is an ideal, and so their sum belongs to P. That means XY belongs to P. However, where is P? P is inside sigma. In fact, that's how we chose P, right? P is a maximal element in sigma. So P is the type of ideals that sigma has. That means inside P, every element is a zero divisor. So this XY also needs to be a zero divisor. So XY is a zero divisor, i.e. now we apply the definition of zero divisor. XY times Z should be equal to 0 for some non-zero element Z in our ring A. Okay. Now what will happen if YZ is non-zero? Then you are looking at a product where one element is X and another element is YZ, which is non-zero, and the product is 0. But then again, by the definition of zero divisors, X is a zero divisor, which it is not, because that's how we chose X. X is an element in I1 which is not a zero divisor. So that means this cannot happen. So YZ needs to be equal to 0. But non-zeroness of Z then makes Y a zero divisor, which is also not true, because just like X is not a zero divisor, Y is not a zero divisor in the ideal J1. That means this thing cannot be true. However, what is the source of this problem? The source is the original supposition that the maximal element P is not a prime ideal. So our last supposition is wrong, i.e. P must be prime, and this is where the solution ends.